There was an idea to bring together a group of remarkable people to see if we could become something more.
In designing the UAS, the team followed a product development cycle to ensure that the system would meet the AUVSI SUAS requirements. In opportunity development, the mission requirements were firmly established and assigned quantifiable performance measures. In concept development, the team divided into 3 sub-teams: airframe, autopilot, and imaging/interoperability, then established subsystem requirements and explored various UAS concepts. After selecting the desired concept, the team moved to subsystem engineering, creating prototypes, models, and simulations to develop and test UAS subsystem performance. Finally, the team combined the subsystems and worked through system refinement, performing mission tests and making small modifications to maximize competition score. The team used a parallel path approach throughout this design process. One path was dedicated to improving autopilot and imaging capabilities on last year's platform, the My Twin Dream airframe. The second path focused on designing and building a custom airframe more suited for the competition needs. Once the new airframe was ready, autopilot and imaging systems would be integrated. Unfortunately, during the system refinement stage of the design process, the custom airframe suffered a devastating crash that would require nearly every major component to be remade. Due to time constraints, the team has decided to not build another airframe as documented in the technical design paper. Rather, they will fly again with the proven My Twin Dream platform at competition.
The My Twin Dream fuselage, while not as customizable as the fuselage previously discussed, is an exceptionally stable and versatile fuselage that is more than capable of fulfilling all AUVSI competition requirements. The airframe is comprised of 4 sections: the main body, which houses the majority of the plane's electrical components, the tail section, and the 2 wing panels. Due to the difficulties in transporting last year's model to the competition, this year's model of the My Twin Dream was assembled with transportation in mind, and can be more easily disassembled. Other major changes between this year's My Twin Dream and last year's version are the new motors, which are better suited to be used with our 4-cell battery and provide greater thrust-to-drag ratio, the Bastler Ace camera with 12.5mm Ricoh C-mount lens, a new camera that offers higher resolution images, along with a new mounting system that isolates the camera in the event of a crash, and the Inertial Sense Micro INS, a GPS-aided inertial navigation system that is far more robust and accurate than last year's system. Other critical components include the Odroid XU4 computer, the onboard processing unit, the Ubiquity antenna, which enables wireless communication between the ground station and the UAS, the pitot tube and 12C digital sensor used to digitally provide the plane's airspeed, the Flip 32 Plus naseboard, which, combined with a custom-made PCB, is used as the onboard autopilot flight controller, FrSky R9 and R9 combo, a 900 MHz long-range transmitter-receiver combo, and the EFLA 405 servoless payload release, which will be used for the water bottle drop during the competition. All of these systems are powered using a multi-star 10,000 mAh LiPo battery. Finally, the autopilot system is run using ROS-Plane, an autopilot program created by the BYU Magic Lab using ROS and augmented by this year's BYU AUVSI autopilot subteam.
In the autonomous flight category, autonomous takeoff, attempted, high confidence. Autonomous landing, attempted, high confidence. Waypoint capture, attempted, medium confidence. For obstacle avoidance, stationary obstacles, attempted, medium confidence. Dynamic obstacles, not attempted. For object detection, localization, and classification. Search area detection, attempted, medium confidence. Off-axis detection, attempted, low confidence. Localization, attempted, medium confidence. Classification, attempted, medium confidence. Autonomous DLC, not attempted. For air delivery, attempted, medium confidence. Throughout the design process, we sought to verify systems such as the autopilot and payload delivery systems to ensure they were feasible approaches to meeting the mission requirements. Computer simulations played a critical part of this verification, allowing us to predict how these systems would act under various conditions. We also conducted low-risk ground tests to ensure some system functionality without introducing unnecessary risk to the airframe and other fragile components. These tests yielded insights into how the system would perform in a competition environment. Finally, frequent flight tests enabled the team to identify and resolve other issues, such as power distribution and occasional telemetry loss. Encountering these issues early has allowed for more thorough preparation for undesired contingencies.
Over the course of the past year, we have conducted over 70 flight tests. The first few flights were mostly under manual control. Autonomous flight was sustained for only a few seconds at a time for tuning. As the aircraft and autopilot improved, the percentage of autonomous flying increased. The last few flights have been over 95% autonomous. The only RC takeovers have been for landing the aircraft. There has been one flight entirely under autonomous control.
The autopilot Ross plane has 6 PID controllers: roll, course heading, pitch, airspeed by controlling pitch, airspeed by controlling throttle, and altitude by controlling pitch. Ross plane uses different controllers depending on the current altitude zone of the UAV. Each controller can be tuned while flying. A GUI is used to change gains mid-flight. Each gain is changed until the UAV responds quickly, is stable, and has low overshoot. Most controllers can be isolated by putting the UAV in a certain altitude zone or by commenting out other controllers in the code. Roll and pitch controllers are tuned first. They are used in every altitude zone. The course controller is removed until the other controllers are tuned. Next, the airspeed controllers are tuned. Airspeed is controlled using successive loop closure. In the climb and descent zones, airspeed is regulated by controlling pitch, while in the altitude hold zone, airspeed is regulated by controlling throttle. While the UAV is close to the desired altitude, it is in the hold zone. In the hold zone, altitude is controlled by using successive loop closure with the pitch controller as the inner loop. Finally, the course controller is brought back and tuned until the response is desirable. From 4 mock competitions, a total of 15 waypoints were attempted. Waypoints were randomly generated in the flight zone. 14 of 15 waypoints were attained with an average missed distance of 14.6 meters. While we were flying the waypoint path, however, we breached the boundaries.
The obstacle avoidance system uses the rapidly exploring random tree algorithm that our team developed. The algorithm creates intermediate waypoints that connect the white initial position of the UAV to the yellow primary waypoint. It expands potential paths starting from the initial position. Paths are added to the tree if they avoid all obstacles, stay within the flight boundaries, and are possible for the UAV to follow. Once the tree develops enough to connect to the waypoint, the path is smoothed. The rough path is represented in blue. Each intermediate waypoint along the rough path is left out to see if it is not needed. The extra waypoints are discarded from the path. The smoothed path is represented in green. Once the algorithm has found the final path, it is sent to the UAV to be flown.
In 4 separate mock competitions, each with 10 stationary obstacles, our airframe avoided 40 out of 40 obstacles.
The team conducted tests regarding image resolution, image transmission rate from the plane to the ground station, and ideal image overlap while searching for objects. Using a depth of field, angle of view, and equivalent lens calculation, we determined the average resolution of objects that the camera will be able to provide. The Basler Ace ACA 2500 60UC has a sensor size of 1 inch and a focal length of 12.5 millimeters. Knowing that the number of horizontal pixels is 2,592 and the number of vertical pixels is 2048, we determined that the camera would be able to resolve images up to 12.64 pixels per foot at a height of 200 feet. Along with resolution, we performed more than 5 test flights ensuring that the image transmission rate was sufficient to give ample overlap of the search area. The average transmission rate was 1 Hz, and the target overlap for each consecutive image was about 50%. After testing, we concluded that the overlap was approximately 37%. Although slightly below the target value, this is still enough overlap to have duplicate images of the search area, thus increasing our chance of detecting every target in the search area. The imaging team conducted a distinguishable colors test to determine how many human distinguishable colors the camera could capture. To do this, the camera took several pictures of a color grid at various distances. These pictures were compressed by the onboard computer and sent to the ground station, where a ground operator determined the number of distinct colors seen in the image. When running this test, the ground operator could distinguish 9 colors on average. Ground operators use a detection and classification GUI to supply the characteristics of each target and submit to the judge's server. This GUI ensures that each image is reviewed by a ground operator, giving us the best opportunity to properly detect and classify each object. Localization of targets also occurs in the imaging GUI. Clicking on a target in an image marks it with a GPS point. A target can be marked multiple times so that the GPS locations can be averaged together and submitted to the judges. This localization is based on image state information and pixel coordinates of the target in the image. Localization error during testing has ranged from 4 meters to 35 meters.
While approaching the air delivery position, Rossplane uses pursuit guidance law. The guidance law converges the UAS's velocity vector to point directly above the delivery position. The estimated missed distance of the drop is continually calculated upon approach. The bottle is dropped when the horizontal distance the bottle would travel if dropped now is greater than the horizontal distance from the UAS to the delivery position. This gives the longest time for the pursuit guidance to drive the missed distance down. The water bottle drop has only been tested in simulation. When dropped from 45 meters, there is an average missed distance of 3.76 meters. We plan on testing the bottle drop performance in the coming week.
So far, the team has conducted 4 mission tests. These tests have consisted solely of flying waypoints and avoiding static obstacles. During each test, we encountered issues prohibiting us from attempting the other objectives. For example, during one of these tests, we discovered our turning radius in the path planner to be too large, making it difficult to track a commanded path and effectively fly over the search area. It also caused the UAS to fly outside the mission boundaries. In another test, we encountered power issues from having all of the components powered on during flight. Yet another test revealed possible GPS interference from the nearby camera. Each of these system flaws has been recognized and accounted for, resulting in better performance with each successive test. In our last mission test, the UAS flew a waypoint path completely autonomously from takeoff to landing, avoiding 10 of 10 static obstacles. In the remaining time before competition, the imaging and payload delivery objectives will be tested and refined. We are confident in our ability to succeed and look forward to competing in June.